Hello, this is the Code Critics. In this episode, we are going to look at data structures in Python and why many people get them wrong. A good approach for finding the right data structures follows the following steps. First, we look at the raw data, understand its content and format. Second, we think about the use cases and rank them. Which ones are common and which ones are rare. 3. We pick data structures that suit the most common use cases. 4. We transform the data from its original raw format into those data structures. Finally, number 5, we implement the functionality to cover these use cases. In practice, however, I see that steps 2 to 4 are often skipped, which leads to overly complex and slow code. We will see an example later. First, however, let's have a look at data structures and some of their properties. Python has 4 basic data structures that are available without needing to be imported. We have lists that are written as comma-separated values in rectangular brackets, tuples with round brackets, sets with curly brackets, and dictionaries that also use curly brackets but contain key value pairs separated by colon. The first property we look at is how long does it take to check if a data structure contains a given value or not. And we are going to use the so-called computational complexity to assess that. A computational complexity of order of 1 means that it always takes the same time, regardless how many items are stored in the data structure. A computational complexity of order of n means that there's a linear dependency and the more items are stored, the longer it takes. In the case of a Python list, the computational complexity to check if a value is in the list is of order n. So the longer the list, the longer it takes. The same is valid for tuples, but not for sets. Here the computational complexity is constant, which means it is very fast to check if an element is part of a set or not, and the time is independent from the number of elements in the set. In the case of dictionaries, we have to distinguish 2 cases, since dictionaries store keys and value pairs. For keys, the computational complexity is constant, but for values, it is linear. So it is fast to find a key, but it is slow to find a value in a dictionary, especially when the dictionary grows in size. Next, we look at the computational complexity of adding or appending an item to a data structure. For lists and tuples, this is of linear complexity, while for sets and dictionaries, this is a constant time operation. Again, sets and dictionaries win over lists and tuples. Finally, we can distinguish data structures depending on whether they store only unique items or not. Lists and tuples are ordered and can store duplicates. In contrast, sets are unordered but guarantee to store only unique items. In the case of dictionaries, we have to distinguish. The keys of a dictionary are unique, while the values don't have to be. Let's solve an example problem to see the differences between data structures and the resulting implementations in practice. Assume we have a movie database stored in a CSV file. Each row contains a user ID and then the names of the movies that the user likes. For instance, user 13 likes Alien, 12 Angry Men, and so on. We consider 3 use cases. First, we want to load the CSV file into memory, but that happens only once. Second, we want to retrieve the movies for a given user, and that is going to be a frequent request. And third, we want to know which movies are shared by two given users. And this again is going to be a frequent use case. For comparison, we first implement a solution that is straightforward but does not use good data structures. So the following code is bad code for the given use cases. The first use case is to load the movie database. The function loaddb does that. It takes a path to the CSV file, opens the file, creates a CSV reader, and reads the lines of the file into a list. When called for the movies file, it returns the data as a list of lists. Note that we essentially maintain the original format of the raw data, which will turn out to be a bad idea. For the second use case, we implement the function movies that takes a user ID and the loaded database. We iterate over the rows in the database, and if the first element of the row that contains the user ID matches the given user ID, we return the remainder of the row, which contains the movies. It is a simple implementation, but the computational complexity is linear, since we have to iterate over all n rows of the database. The last function we implement is shared, which returns the names of the movies shared by two users. As you can see, we use our movies function to retrieve the movies of the two users, and then two nested for loops to collect the shared movies in a list. Since the movies function is of linear complexity and we're calling it in two nested loops, the shared function has quadratic complexity. Consequently, this code will be very slow for a large movie database. Also, there are other issues with duplicate user IDs or movie names. Now let us do this properly. First, we have a look at the preferred properties of the two most common use cases and find the best matching data structure. For the shared function, we want to check as quickly as possible if a given movie is contained in a collection of movies. So order of 1 computational complexity for the contains operation would be great. The collection of movies is constructed while loading, and that is not a frequent operation. We therefore don't really care and leave the requirements for the append operation empty. However, we would like the collection of movies to contain only unique names, and therefore we put a yes for unique there. If we compare our feature request for the shared function with the properties of the data structures, we find set and dictionary to be the best fit. Since we have movie names only and no key value pairs, we pick the set as the best fitting data structure. Next up is the movies function. We want to retrieve the movies for a given user as fast as possible. We put order of 1 for the computational complexity in the contains column. Similar to the shared function, we keep the requirements for the append operation empty, since that occurs only at loading time. We also want to ensure unique user IDs and put a yes in the unique column. The best matching data structures for the shared function then are again set and dictionary. But in this case we pick dictionary, since we want to store the movies for a user. In summary, our data structure is going to be a dictionary with user IDs as keys and sets of movies as values. Here now the good implementation using the data structure we identified before. The loading function is almost identical to the previous implementation, but in the last line we use a dictionary comprehension to create our data structure. Note that the movies for a user are stored as a set. Loading the movies file and printing its contents results in the desired dictionary with user IDs as keys and sets of movies as values. Retrieving the movies for a given user is now very simple. We only need to call get and provide the default value of none in case that the user ID is not in the dictionary. This is an order 1 operation and is much faster than the previous implementation, especially for larger databases. But it gets even better. The shared function is now a one-liner that computes the intersection of 2 movie sets. Set intersection is of linear complexity and again a large improvement over the quadratic complexity of the previous implementation. So by picking the right data structure, the code became shorter, simpler and much faster, especially for larger databases. Some final tips. First, don't jump right into an implementation, but think about the most common use cases and identify suitable data structures first. This generally leads to simpler, faster and more robust code. Sets are very useful, very fast, but often neglected. Keep them in mind. If you end up with a dictionary of dictionaries or even more deeply nested dictionary structures, that is usually a bad choice. Rethink. And finally, prefer tuples over lists, since tuples are immutable and therefore safer to use than lists. I added some links to the description that provide more details on immutable versus mutable data structures, computational complexity, and list or dictionary comprehensions. And that's it. Thank you for listening.